I'm Bryan Holler. I am starting my 5th year of grad school here at the University of Colorado in the APS department, so astronomy or astrophysics and planetary science. I work with Leslie Young at the Southwest Research Institute. She's a deputy project scientist on New Horizons. I will not be presenting New Horizons data. I am not on the mission. I'll be presenting ground-based observations of Charon, which are pretty hard to come by. And this picture is a combination of Pluto and Charon, a yin-yang pattern, showing that they're two sides of the same thing. They're very different, but very similar. So a little overview of what I'll be talking about. Charon is the largest moon of Pluto, but they have very different surface compositions. Charon is primarily covered in water ice in both crystalline and amorphous phase, as well as ammonia hydrate. Pluto is covered in relatively volatile ices, molecular nitrogen, methane, and carbon monoxide. And it took the New Horizons mission to actually detect water on the surface. It has never been detected in ground-based spectra on Pluto. It's one of only 2 objects in the Kuiper Belt where ammonia has been detected, the other one being Orcus. The high crystalline water ice fraction is kind of strange on Charon. We'd expect, so crystalline water ice is the kind of ice that you find on Earth primarily, in your ice cube. It's well-ordered crystalline matrix. When it interacts with radiation or cosmic rays, those bonds break and you get an amorphous solid, sort of like glass, where there's randomly oriented molecules in the solid. So you expect over time, you lose the crystalline water ice, you gain more amorphous water ice. That doesn't appear to be the case on Charon. We also, because we detect ammonia on the surface, as well as crystalline water ice, has been put forward that there's some sort of resurfacing mechanism, such as cryovolcanism, going on Charon. I'm here to tell you that I think we don't need cryovolcanism. It can be explained other ways. So Charon is not active. And I apologize to Mark, who's going in 2 talks from now. Based on his talk title, it seems like he's going to be talking about how Charon is possibly active. So Charon and Pluto formed in the same a giant impact. So you have proto-Pluto, proto-Charon. You have a grazing collision that results in the formation of the system we see today, which has 5 moons. 4 of them are tiny, likely formed from a debris disk of ice after the formation of the other 2 objects. But after this point in time, they have followed very different evolutionary paths. Even though they share the same orbit, same radiation environment, they have very different surface compositions, very different histories. So when I was looking at all the talks, I saw people were probably going to talk about how they went to really cool places. So I felt like I needed to represent the observational astronomers. I went to Hawaii last year for 50 days to get all this data. And I used Keck 1 to obtain this data. And one of the nights I was there was July 14th, 2015. And that was the date of the closest approach of New Horizons to Pluto. The image up there was the data that I was taking at the exact moment of the flyby. The rotation period of Charon and Pluto are about 6.4 days. So the 4-hour time difference, or the light travel time, didn't really make much of a difference. So we were observing the same hemisphere of Pluto that New Horizons was. So that's something I'm very proud of that I was able to do, because I wasn't on the mission. So the data that I got are spectral data cubes. So I like to think of them as a loaf of bread. So if you take a slice out of a loaf of bread, you have a 2D slice, and that slice corresponds to a particular wavelength. So if you look at the bread loaf long ways, you're looking, you get an image. But if you look at it sideways, you get a spectrum. So we had 6 nights between the 14th of July and 30th of August, all at centered on different sub-observer longitudes. So you're looking at different parts of Charon's surface during each night. And we obtained these in the near infrared using adaptive optics And as you can see here, Pluto and Charon are fully separated. Pluto is the bright one on the bottom. Charon is the dimmer one on the top. This is hard to do because they're separated by less than an arc second. It's really tiny on the sky. So hasn't been done too much before. And here is what you've all been waiting for, squiggly lines. So this shows this is the average spectrum of Charon. It's still a little ratty because Charon is so faint. But we see signatures of amorphous water ice, crystalline water ice, and ammonia hydrate, as well as this darkening agent that nobody's been able to effectively model at any point in time. We have no idea what that is. This feature here, 1.65 micron band, is unique to crystalline water ice. It does not show up if there's only amorphous water ice. So what I did was I fit Gaussians to this band and to this band to determine properties of the species on the surface. In particular, the 1.65 micron band is temperature dependent. So it depends on, so the central wavelength of the band depends on temperature. So you can use that as a gauge of what the surface temperature is. And for the ammonia hydrate, I wanted to figure out particularly the integrated band area, which is sort of like an equivalent width and gives you the amount of the stuff on the surface. That's what it's related to. So, and then use the 6 nights that we have to determine longitudinal variability. How does this stuff vary across the surface? There's some limitations to this. In particular, you're adding a lot of noise when you're trying to get the spectrum from the data cube. You're adding way more pixels in each image than you would if you were doing long slit. So you're making it noisier. However, because of the small separations, this is one of the only ways to do this from the ground, to get a separate Charon spectrum. And the temperature calculation is not very precise. However, we do end up in agreement with other values determined previously. So here's some results. They're not terribly exciting because of this noise, the lower signal to noise. We're looking at temperature as a function of longitude. The red solid line is the average surface temperature. So that's 41 Kelvin. And the dashed lines show the uncertainty. All of the values are consistent with the average value and with each other. So no difference in surface temperature across the surface. This is important for determining an active site for cryovolcanism, possibly. You'd expect a warmer part of the surface for where cryovolcanism is currently going on. And here's some plots for the ammonia hydrate band. We see a similar thing. There's no difference in the amount of ammonia hydrate across the surface of Charon within our error bars. And I point to, with this big arrow, to the one down here, which is the band area, which gives you the amount of ammonia hydrate on the surface. It appears to be constant. And I'll point out something, although it may not be statistically significant. If you look at this shape and this shape, so if that ended up being real, that would be pretty interesting. We need to find a way to beat down the noise. So from New Horizons, the youngest surface age is 4 billion years. So everything is older than 4 billion years on Charon. Based on laboratory data, you can get crystalline and amorphous water ice reaching an equilibrium over time. This happens on the order of even 500 million years after the ice has been placed on the surface. So even though the radiation is coming in, destroying the crystalline water ice, it's thermally recrystallizing based on temperature. So even for temperatures of 30 Kelvin, you get this in less than 1 billion years. And the temperature determines how much crystalline water ice remains. And it's possible that ammonia is diffusing through the surface ice to remain on the surface, because it should be destroyed on tens of millions of years timescale. So there is a replenishment process for that, but it's likely diffusion. And if, if this similar shape for these is real, that would mean that areas where it's warmer, you're getting more ammonia, which means you have faster diffusion rates because of the higher temperature. So applying this to the rest of the Kuiper belt, crystalline water ice has been detected on a bunch of other bodies, including Haumea, Quawar, and Orcus, as well as Haumea's moons, Namaka and Hayaka, and the Haumea collisional family. Some of these objects are extremely tiny, maybe 170 kilometers across. You would not expect cryovolcanism resurfacing to go on a tiny object like that. And Orcus is the only other object where ammonia has been detected. So we can apply what we've learned about Charon with New Horizons, these other objects that we probably will never go to, and say that cryovolcanism or other replenishment processes are not required to explain the surface compositions of these bodies. So additionally, no apparent energy source. Radiogenic heating should be pretty low for Charon, and tidal heating should be negligible because it has a nearly circular orbit around Pluto. So you have no possibility of an energy source, likely no ocean or liquid water under the surface, so no life as we know it. Pluto, however, could be a different story, and I provide a segue to Maya's talk. If you don't like the pun, if you don't like it, I can meet you outside later. So I'll leave you with a haiku and take any questions.
So I actually agree with you. I think it's unlikely that Charon has an ocean today and that it has cryovolcanism today, and you guys will see. Just a comment about the difference between Pluto and Charon, and I guess it's also for the next speaker as well. Isn't the reason why their surface and the fact that Pluto has an atmosphere, isn't the reason for the dichotomy simply that Charon has a lower gravity and so doesn't hold on to any gases that would come out of it?
Yep, that's the explanation. It's pretty simple, but they started in the same spot, and this is important for detecting things such as non-methane hydrocarbons potentially on Charon. At some point in the past, it might have had these volatile ices, but they were lost. And during that time, you can get ethane, ethylene, acetylene on the surface, if it ever had an atmosphere. So.
Other questions? All right, we'll move on.